Hi, ladies and gentlemen. So we are continuing to take a look at oceans. Remember, this is Oceans Part 1. And so after this next section, we've just finished taking a look at the seafloor and at ocean water chemistry. And now we're going to take a look at ocean waves. Following that, we'll wrap up Oceans Part 1 for us, and we'll have a test over that before we get into Oceans Part 2. So ladies and gentlemen, we're going to start taking a look at waves, wave action. Specifically, we're going to spend most of our time taking a look at what we call surface waves. And so we're going to take a look at how it is that surface waves form. Most of the waves that we think of as being ocean waves form as wind blows across the surface of the water. And so air is made up of air molecules, things like oxygen and nitrogen and things of that sort. And when those molecules hit the molecules of the water, the energy from those air molecules moves into the water molecules and causes them to start moving. It's a little bit like if you are moving down a very crowded hallway and you bump into one person, that person is going to then gain some of the energy from your movement. It's going to cause them to stumble and move a little bit, and they might bump into somebody else who might bump into somebody else, and it becomes kind of a chain reaction. And that's kind of what happens when the wind moves across the surface of the water. There's friction between the air molecules and the water molecules, and the air molecules end up bumping into those water molecules that are up near the surface and pushing them. And then those water molecules push other water molecules, and you end up with a wave. So it's basically energy moving through ocean water that comes from the energy from the air. So what is it that determines the size of a wave? There are basically three things that determine how large a wave is going to be. So the strength of the wind, or sometimes we call that the wind speed, that is one of the things. The stronger the wind is, or the faster the wind is, the larger the waves that you are going to have, the more energy that is being transferred into the ocean water. How long does the wind blow for? In other words, what length of time does the wind blow? Does it blow for a few hours, or does it blow for several days? Over the open ocean, oftentimes wind can end up blowing for several days very consistently. And then the final thing is the distance that the wind blows. Was there a large amount of open ocean over which the wind was able to blow? Did it blow for miles and miles and miles without being interrupted by a piece of land or something like that? Or did it just blow for a short distance? The longer the distance that the wind blows, the larger the wave. So the stronger the strength of the wind, the bigger the wave. The longer amount of time that the wind blows, the bigger the wave. And the longer the distance that the wind blows, the bigger the waves. We have talked a little bit before about the parts of a wave. And so we talked about the fact that there's a crest and a trough, the crest being the high point of the wave, the trough being the low point, that the distance from one crest to another or to the next one is the wave length. We talked about the distance between the crest and the trough. That is the wave height. We also talked about the wave base, which is the point at which no more water molecules are moving because of the energy from the wave. And to get to the wave base, you take 1/2 of the wavelength and you go that deep into the water from the kind of sea level point. Go that far into the water, and that is your wave base. And so water particles, remember we said that waves are caused when energy from wind, the air molecules kind of give some of their energy to the water molecules. Up near the surface, these water molecules move in a pretty big circle. So, whoops, I was thinking I had a little bit bigger picture there. But so the water particles just kind of move in a circle. Think of a buoy going up and down and up and down. The water particles are doing the same thing. We typically think that the water particles are moving toward the shore, right? So this arrow tells us up here that the water, or that the wave is moving in this direction. So shore must be over here somewhere. We typically think that water is moving closer and closer to shore. Well, if that were the case, like, the land would eventually be overcome by all the water that's moving towards it. Instead, what is happening is the water molecules really aren't moving all that far. It's just an up and down motion, and we see that up and down motion in the waves. And so the water molecules move in these circles. The deeper you go, the smaller the circles, until you finally get to the wave base, and below that wave base there are no more circles that the water molecules are moving in, because the energy doesn't reach down that far. All right, so as I mentioned a moment ago, although it kind of appears that the waves are carrying the water towards shore, it does not actually do that, at least not when we're out in the deep ocean. Things do change a little bit as you get closer to shore, but out in the deep ocean, the water is not moving towards shore. It's just moving in that up and down circle. And as we pointed out a minute ago, the larger circles are closer to the surface because there was more energy there, because it was closer to where the energy came from. The deeper you go, the smaller the circles become. And then we talked about the fact that when you get to a depth finally of 1/2 of the wavelength, then the water particles are no longer moving because of the wave action, or because of the wave energy. Here's that close-up picture I was looking for. So here you can see those circles. Again, it's just like the buoy, just moving up and down, not continually traveling towards shore. All right. I said that that's what happens out in the deep ocean, but things do change a little bit as we get closer to shore. As the water gets more and more shallow, that energy is going to start actually reaching the bottom, and we say that the wave feels the bottom, and so as the wave approaches the shore, the water becomes more and more shallow, all right, which makes sense, and then that causes the wave to actually grow taller, because it's kind of pushing the water up from the bottom. So near the shore, the wave height actually increases, the wave gets taller. The wave length actually decreases, the waves actually get closer together. So here we kind of have a diagram that can explain this. So as you get closer to shore, all these little circles that the water molecules were moving in, suddenly some of those circles are starting to run into the sand at the bottom. Technically speaking, the sand is running into it, but there starts to be friction between the water molecules moving down here at the bottom of the wave and the actual sand down at the bottom of the ocean. And so these circles here kind of get squished, and the wave gets pushed up. And then on top of that, these waves this energy here kind of gets slowed down because it runs into the sand. So it's like, here we're going to stop. However, you have the energy that is moving up at the top of the wave. This kind of slows down here, but this is still just trucking right along, moving right along. And so there's nothing slowing it down up here at the top. And so the wave actually starts to bend as the bottom slows down and the top keeps going. And eventually you end up with a breaker where that wave is curved right over, and the top part of the wave actually becomes too heavy and it actually crashes down. And that's our breaker that we often think about when we're standing on the shore and watching the waves break. Also, a little note here, we talked about the fact that the closer to shore you are, the wave height increases and the wave length decreases, because when we were out to sea, the wave height is actually shorter or smaller and the wavelength was larger. All right, a little obligatory sunset picture, just because sunsets at the ocean are beautiful. All right, so ladies and gentlemen, how do waves actually affect the shore? All right, the waves can actually change the shoreline, and so we're going to take a look a little bit at how that happens and why. So as a wave comes onto the shore, it actually pushes water, or the water washes up actually at an angle, and when it does, it carries some sand and pushes some sand with it, because there's energy there, there's force. And so just like the air molecules, hit the water molecules when it was windy and caused the water molecules to start moving, or started to put energy into the water to cause movement, so that we have waves. It's similar with the waves then, or the energy from the waves then hitting the sand and causing that to move. So the sand starts to move. And so when the water comes in at an angle and pushes the sand, then we know from standing on the ocean's edge and watching these waves, the water then kind of washes back out again. And when it does, it kind of goes straight back down the beach toward the water. Gravity causes this. And so as the sand keeps going up and down the beach, we call this longshore drift. So here's a picture where we have sand, and maybe there's a bunch of sand here, and as the wave comes in at an angle, so here's the angle, here is the shoreline, so you can see that there's a bit of an angle there. And so as the wave comes in, it pushes the sand at that angle, and then it kind of washes straight back, and then it pushes at that angle, washes straight back, pushes at that angle, washes straight back. And as it does, it's carrying that sand down the shoreline. All right, so we're going to kind of see what that looks like here in this little animation. So we've got the dot represents 1 grain of sand, so to speak, and what's going to happen to that. As we see the wave slowly making its way towards shore here, it's coming at an angle, and the breaker happens and pushes the little grain of sand, and then that little grain of sand ends up washing back a little bit because of the gravity backwash of the wave. And then it continues to happen as waves come in towards the shore, and it continually pushes that grain of sand down. Well, it's not happening to just one little grain of sand, it's happening to many grains of sand as those waves come in. And so it's pushing a lot of sand down the shoreline. And that can create things like sandbars. All right, I'm sure many of you have seen sandbars where the sand seems to be sticking up above the level of the water at times. Sometimes you can have underwater sandbars as well, where the sand is built up, but maybe not to the point where it's above the water line yet. One of my favorite beaches in the world is up the coast a little ways in Maine. So it's called Popham Beach. It's about an hour to an hour and a half from my house, so it's probably 2.5 hours from the Dover area. But there is a sandbar right in this area here. So you can see there's an island. Here's the beach right here where I typically like to go. And at low tide, there's actually, like, the shore looks a little bit there, the beach looks a little bit more like this, because this is all sand here. There's a sandbar here at low tide, but when the high tide comes in, it gets covered. And so at low tide, you can walk out here to this island and walk around and climb on the rocks on the island. But at low tide, before high tide comes in, you have to get off the island and head back to the main part of the beach, because this whole section here soon is underwater. And another cool thing about this beach, just the way it's shaped, the waves tend to come in at an angle like this here, and kind of at an angle like this here, and so they can run into each other, and that's what kind of gives it this pointy shape here, and why the sand tends to build up in this area right here. So it's a pretty neat little beach. All right, so as the waves kind of slow down, they deposit their sand, and that's kind of what creates the sandbar. We can see a sandbar here underneath the water, kind of in this area. There's another one, you can kind of see it underneath the water in this area as well, where sand has built up. You can imagine that people who have spent a lot of money to live right on the beach don't really want their sand all washed away, right? And so a lot of times there are efforts to try to stop beach erosion and stop the sand from being moved down the beach toward other places. And you can also imagine that people who live down the beach a ways don't want their house to suddenly be covered with sand from all the sand that's being washed down to their end of the beach. So a lot of times people will build these walls to try and stop the sand from moving too far down. It has a very strange name, these walls, which can be made of wood or rock or cement. They're called a groin. Again, very strange, but here's what one looks like. This one is made of wood. And so you can see that the waves are kind of coming in at this angle, which is kind of pushing the sand slowly down this way. You can see that the sand is built up along the wall quite a bit here, but on the other side of the wall, where now the sand isn't getting pushed over there anymore, the sand is further back. You can probably also see, however, the sand is getting higher and higher here on this wall, and eventually, after enough time passes, the sand may just go right over that wall. So you can see that these have to be probably rebuilt on a regular basis. A wooden one is going to wear away and get knocked over more easily. Stone and cement will last a little bit longer, but still they're a temporary fix to the problem because the natural process of sand moving is going to continue to happen. One thing that can happen because of these sandbars are things called rip currents, and rip currents can become very dangerous. As the sandbar actually gets larger, it can sometimes start to trap some of the water and not allow it to flow back out to sea again. And so eventually the force of that buildup of water kind of breaks away part of the sandbar, and it creates what's called a rip current. And the reason we talk about them is because they are dangerous and they can happen near the shore, and swimmers sometimes get caught in these rip currents, and they can end up drowning if they don't know what to do. So we're going to take a look at a diagram here. So here we see a sandbar that has built up over time, and as the water comes in the waves, and then washes back out, you can see in this area it's going to get kind of trapped. And then eventually that water, because water can be very forceful, it pushes its way through here because they found a weak place in the sandbar and pushed the sand out there. Now the water's rushing through here very quickly because water goes through small openings very, very fast. And so if somebody is swimming over here, so here's our little swimmer person. All right. And so they're swimming in the ocean and they get carried out this direction. If they try and turn around and swim back towards shore, they're never going to make it because the strength of that rip current is just too strong. What they really need to do is move this direction to get out of the effects of the rip current. And then once they've gotten out of those effects, then they can move back towards shore where the water's not moving as fast. All right, keep that in mind when you are at the beach. All right, ladies and gentlemen, you have a great day.